Okay, let's get started. First of all, several announcements. We posted homework 2 before, I think, last weekend. So some of you are using a new Mac computer, which is ARM-based, not really Intel-based. So you cannot run virtual machine on that. So if it is that case, please contact us. We will give you a different instruction so you can run this on your new MacBook. So the course evaluation, the midterm course evaluation started yesterday. So if 90% of the class submit a review, then everyone gets 10 bonus points. I think it ends in a week. So you have a week to earn that 10 bonus points. So this Wednesday, I will be out of town again. So sorry about that. So I will deliver the class online again on Friday night. So we will continue to talk about access control Friday night. Also, next Wednesday, we will have an in-person midterm. All of you have to be here to attend the midterm, and you also need to bring your UBID or check ID. Tomorrow, I will post the preparation guide for midterm. I will basically list, you need to understand this concept, you need to understand why this one is secure, those kind of things. So I will post that tomorrow. Okay. So today we will talk about access control, and we will spend 2 classes on access control. So far, we've been talking about applied crypto, we've been talking about authentication. So access control is a really big term. Technically, everything we are doing in security, we are doing access control. We are trying to prevent attackers from accessing some kind of resources. So that is access control. So in 2 sessions, we will talk about some access control principles, some access control technologies, and different access control models. For example, access control matrix, access control list, capability tickets. So different access control models, discretionary access control model, mandatory access control model, role-based access control model, and also the most recent attribute-based access control model. So role-based access control model has been a hot topic in academia, in industry for 20 years. So most of the systems we are using, if you go to big companies, the system you're using use role-based access control. Your personal computer more likely using discretionary access control, and military computers, they use mandatory access control. So we will discuss the differences, how they are implemented. So like I said, I mean, the term access control is really broad. It's about the prevention of unauthorized use of a resource or use any resource in unauthorized manner. So if you look at this, that's a very broad definition that covers everything about security, actually. So in this class, we will talk about some specific notions of access control models. And an access control model specifies who is allowed to access what resource and what type of access is permitted. So some modern models can even specify when the access is permitted. So access control is really a difficult problem, actually, because there are so many different objects, subjects, they are interacting with each other, and there are so many types of permissions. So access control obviously is related to authentication. We talked about authentication last week. However, authentication is more about prove someone is whoever he or she claims to be. Prove someone's identity. That is authentication. Then access control is also related to another concept called authorization. However, authorization usually happens before access control. Authorization is about someone give a subject give other subjects some permissions, some rights to do something. But access control is more about the runtime to enforce that authorization policy, to at the runtime to really check if a subject has the permission to do something. Whether that subject has the permission to do something is specified beforehand in authorization. Okay. It's also related to audit and integrity protection, systems monitoring to ensure proper use of resources, compliance with policies. So sometimes you feel those concepts, authentication, access control, authorization, they have been used interchangeably. There is no clear boundary between them sometimes. But in this class, we are trying to separate. They have different meanings here. So in access control, like I said, it's more like a runtime check, right? So the entity that does the runtime check, usually we call it a reference monitor. So this is a concept proposed in an old paper. So this reference monitor will mediate the access to resources. Complete mediation means the reference monitor will control all access to the resources. So let's say in this figure, it's more like the operating system. In our operating system, you log in as a user. When you log in, there is actually an authentication there, right? To prove you are you, to prove you have, you can even use this computer in the first place. After you log in, the computer actually has many different users, not only you. And every user has different permissions. And the root can give each one different permissions on different files. So that process, the root give permissions to different one, that's kind of like authorization. But when you actually access a file, you want to open a file, you want to execute a program, the operating system will check if you have the permission to open that file, or the process running on behalf of you have the permission to open a file or run a program. And that process, we call it access control. Okay. So if we simplify this, we can say the subject here will be user process. The user process wants to access some resource. Could be file, could be a pipe, could be many other different things, a socket on our operating system. Then the reference monitor, in this case, is part of the operating system, will check if the user process has a permission to do that. So when we design access control models or reference monitors or design those policies, there are a lot of principles. One of the principles is least privilege. Basically, the least privilege principle is about each entity should be granted the minimum privileges necessary to perform its work. So in our operating system, the CPU has multiple layers, like an x86 CPU. We have ring 0, we have ring 1, ring 2, ring 3, right? Well, now we have ring -1 to run hypervisors and other things. So in ring 0, we run the kernel. So the kernel here is a subject. The kernel can access all kinds of resources. And the kernel should be able to access those resources. Otherwise, our computer will not work, right? So, however, on top of the kernel, we run all kinds of applications. Those applications run in the user land, run the CPU level ring 3. At ring 3, you cannot execute all the CPU instructions. Some of the instructions you can only execute at ring 0. Some of the instructions you can only run in ring -1, right? So by doing this, we do not grant the applications permissions it doesn't need. If the application wants to read from the hard disk, the application has to go through the kernel. The kernel will read the hard disk and give that to the application. The benefit of this is even if the application is malicious, it will only be able to do limited damages. If the application crashes itself, it will not crash other applications because it doesn't have the privileges to crash other applications. So those are one of the design principles, least privilege. A lot of what we're doing today is still try to apply the least privilege principles to existing systems, so to make it more secure. Also, separation of duty. This is a practice of dividing privileges associated with one task among several different individuals. So we will not have the single point of failure. If one entity is compromised, our whole system will not be compromised. So this basically limits the damage a single individual can do. Okay. So 3 important concepts in access control. The first one is subject. So subject is an entity that may obtain access to some kind of a resource. Then that resource in this scenario becomes an object. Then we can also have many different types of access, right? So that's called access right or permissions or privileges. For example, you can do a read, you can do a write, execute, delete, search, many different things. Okay. So let's go back to the operating system example. So what are the subjects? Most people were saying the user will be subject. But actually from the operating system point of view, the subjects are mainly the process. But each process is associated with a user. For example, in Unix, each process has a UID, has a group ID, has a user ID. So it is associated with a user. So a process can do many things. A process can open a file, can read a file, can delete a file, can add things to a file, to write to a file, right? So all of those are just different access rights. Then the objects here, there are many things. First of all, like a file, I just said, and also a process itself can be an object. One process can kill another process. When you run Linux, if a process is hanging, what do? You use the kill command. You get the PID of that hanging process, then you use kill command to basically send a signal, ask the kernel to kill another process. So in this case, the process you want to kill is an object. And you have the permission, you have the access right to send a signal to kill that, right? So process itself can also be object. There are many different objects in operating system, files, directories, devices, peripherals, pipes, sockets, everything you can act upon, those basically are objects. Then after we have those 3 things, subject, object, and access right, then we can have a rule. The access rule is very simple. It could just be, can be read like subject S has some kind of access right to an object O. That's just one rule. And there could be many rules in one system. So how do we represent those rules? One way to present this is using something called a matrix, access control matrix. This is very easy to understand. So the columns are just different objects, all the objects in the system. The rows represent all the subject, and each cell there represent the rights the subject has on the object. For example, we have a matrix here to represent whether users in a university can make phone calls. So in this case, the object here, we can divide them into the internal phone calls. Internal means inside of the university, on campus phone calls, then no-call phone calls, like the Buffalo area, the non-distance phone calls, and international phone calls. So those could be object. Then the subject here are just the public, anyone on campus, students, staff, administration. Then we can say for different users, they can have different rules. For example, the administration, they can make international phone calls, they can receive international phone calls, or some other permissions. So what's the problem of this approach? The approach is, this is like a global access control matrix, which has everything, right? So it will be a huge table. However, this table could be a sparse matrix. Many cells there may do not have any information, which means there's no permission for some subjects to work on a lot of different objects. Because maybe one subject will never work on those subjects. So it will be a sparse matrix. If you want to store such a matrix, it will be very expensive in storage, right? So another way to represent those rules is using something called access control list. So we do not really store a matrix like this. For example, the Linux we are using, or Windows you are using, we do not have a matrix like this. We store something close to access control list. So Linux doesn't really use access control list. The extended version does. The default one we're using is a simplified access control list. So let's say if we have our access control list, the access control list is, like the name suggests, is a list. This list should be stored with an object. So this list specifies all the subjects that are authorized to access the object. So basically, it's kind of like a column in this matrix, but that column is not stored in a centralized place. It's stored with each object itself. For example, if we use the access control list for the telephone system, then we can say the object is internal on-campus phone call. Then we can say the subject, public, means everyone, will be able to make the phone call, receive phone call, and also transfer, blah, 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 right? So this is a list, has every subject's ID and also every subject's permission on this object. So this is similar to what we are using in the Linux or Unix file system. But next, let's take a closer look at how the Linux file system permission works. Then we compare this approach, the Linux approach, with the ACL approach, so to say if they are the same thing. So in Linux file systems, the default one, we first define 3 different user groups. The first one is just owner. Owner is the file belongs to the owner. Usually, who created a file automatically becomes the owner of the file. There are several bits of owner permissions, and those owner permissions only applies to the owner of the file or directory. Then the second user group is called just a group. So this is a group, and a group can have many different users, and all users belong to this group will have the same access permission privilege to a file. then there will be everyone else. So you can see the subject here is not everyone on the system, not that level of granularity. We divide just for each object, a file, we create 3 user groups for that file: owner, group, and everyone else. We do not create a permission access control right for each user on the system. Okay. Then the Linux file system only support 3 permission types. One is read, to grant the user or the process created by the user the ability to read the content of file. Write permission to modify or write to a file, and the execute permission to allow a user to execute a program in the file system. So here is an example. Let's say this is my old laptop, and I'm do a listing on my home folder here. So you can see those are the files on my file system in my home folder. And the left-hand side, you can see there is a column. The column has like 10 columns. The very first one is either dash or D. Dash means this is a file. D means this is a directory. Then we have 9 columns there. They could be only 4 possible values. First one is R, means read. W means write. X means execute. Then dash means no permission, right? So those 9 columns basically are the permissions for owner, groups, and others. The first 3 columns for the user, the second 3 columns for the group, and the last 3 columns for everyone else. Then going back to this, so at the end of this, obviously you can see the file name, right? Then in the middle, you can say there are 2 columns. In this case, both showing Zeming here, but the first one is actually the owner. So who owns this file? The second one shows the group. In this case, I didn't specify a special group. That's why the default is also Zeming here. File size, time, and file name. So what does it mean here? Let's say the first one, there is a PDF, 14-P2P PDF. For that PDF file, this file belongs to the user Zeming here, and the user Zeming has the permission to read this file, write this file, so I can change that, but I cannot execute this file because it's not really an executable anyway. Then for group is also Zeming. In this case, the permission is also read and write. Then for everyone else on this Linux system, there are many other users on the Linux system. Their permission is only read. They cannot write to this file. They cannot change. Then there is another one, for example, let's say if I have an executable file here, we don't have an executable. Those are directories. So the executable here means you can enter that directory. So there is another file. I don't know what this file is. AML file. So this one, I can read write. The group can only read. Everyone else can only read. Okay. So that's the Linux file system, the default one. Okay. So now we can think, if this file system is an access control list, this is very similar to the access control list we talked about. First of all, this meta information is stored with the object, with the file itself. It is actually stored something called inode. Okay. But we don't need to go that far. It is stored with the file. It's not like a centralized place in the kernel to store this. Second, it does specify the permissions for several different user group, and everyone else. However, if we go back to previous access control list, you can say, we want that permission to be more fine-grained. Usually when we say access control list, we want the policy to be very fine-grained. We should not have group or everyone else. We should have the permission for every account, every user on the system. So for a Linux file system, you cannot do that. Let's say you have 3 users or more users, and you want to set a different permission for each of them. It's very hard to do that in Linux, okay? Because it's not a fully functioning access control list. That's why many years ago, people have been extending Linux to support the access control list system. So it will allow very complex permission structures beyond the basic default ones. There was a paper published in Unix ATC 20 years ago. ATC stands for Annual Technology Conference, I believe. It's one of the tier 1 or tier 1.5 conference in operating system design. So in that paper, POSIX access control list on Linux, they basically implemented and presented a system to have a fully access control list on Linux. And this system is it's actually available on most of your Linux boxes. So if you use Linux, you should have this. Let's say, so this is my default Linux box, and I just use it for everything. Let's say we do a ls, then we can say all the permissions here, right? So this is a default view. But if we do, what's that called? Set, I believe is this. No. Anyone use this before? What? F. How do I spell that? CL? Just this? Oh yeah, you're right. So then we can do get, right? So let's say if we do a get, we can do any file here. So you can say that we can do more fine-grained access control here. It tells me the user group and other, because I didn't set more fine-grained. But if I did set that, it can be different users, different groups, and everyone's permissions here. Okay. So to set the permissions, you just need to do the set facl command. To get that, you just use the get command. So this was proposed back in those 2003 paper, 20 years ago. Okay, so we just said that the access control list is actually the columns of the access control matrix, and we pick one column and store that with different subject, right? So a problem with this approach is it's difficult to determine what privileges a subject has. Guys, please be quiet, okay? So the problem is because the information is stored with all the objects. So how do you know if you want to know for a subject what permissions he or she has, you have to go through all the objects in a file system, right? So it's not very good if you want to know what privilege a subject has. So another approach is we do a reversed way. This way we call capability list. It's not access control list. It's capability list. Basically, for each subject, we store the row of that access control matrix. Going back to the telephone example, then public is the subject here. The public can only do internal calls, can receive internal calls. The students can do internal calls, local calls. They can receive long-distance calls, right? So in this case, the permissions are associated with the subject, and this is called the capability list. So another way to store this is something called the access control triples. This is basically a something in the middle of a capability list and access control list, and also access control matrix. The problem of access control matrix is a big table. There are if there are n subjects, there are m objects. So the table has m times n size, which is huge. And we know that the table is sparse anyway. So what if we just have a much smaller table? In this table, we do not store everything. We only store those rules that subject has a permission to something, right? So basically, we only store. So where are the sounds come from? Well, if you don't want to learn anything, you can go. I don't mind, okay? I just don't want you to waste the other students' time, okay? So then we can have a table. So in this table, it's not m times n. It's just a list of those rules. So we can call it a rule list. We can call it a policy with different rules, right? So the example will look like this. We have subject, we have the access control permissions, we have object. So the public can have the core permission to on campus. Public can receive calls from on campus calls. So this is a structure we use very often in real world designs. Of course, Linux right now we're not using something like this. Okay. So we have looked at two extremes. One is ACL, another one is capability list, and the choices of using them may affect many aspects of the system. So ACL systems usually need a namespace for object and subject, while a capability ticket can serve both to designate a resource and to provide authorities. So let's look at our first access control model, which is called DAC, DAC, Discretionary Access Control Model. So in this access control model, the subject can grant privileges to other subjects. So let's say we have a predefined access control matrix to define all the permissions for the object and subject in the system. But if this can be changed by some subjects, this is called a discretionary access control. Linux is an example of this. In Linux, you create a file. You can use command touch to create a file. After you create this file, you can change the permission of the file. You can, because you are the owner, you can even change the owner of it, right? So because you are the owner, you can change it. Then this is called discretionary access control. So in our real world, a lot of our personal properties, the access control we are doing is, we can say it's discretionary access control. You bought a book yesterday, and your friend asked you if he can borrow your book, and you gave the book to your friend. So you are still the owner of the book, but now your friend has an access control permission to read that book. Only because you give the book to him, because you are the owner, you allow that. So that is kind of like the discretionary access control, right? This is different from something called a mandatory access control. So in mandatory access control, users are granted privileges at the beginning. Then after that, it's fixed. No one can change that, and no one should change that. So formally, let's say we use this triple SOA, subject, object, and access control permission to represent an access right. Then at a particular time I, the state of the program, X, the state of the system, Xi, can be represented as many different policies like this, different rules of like this. Then the system can have many different transitions, maybe adding a user, maybe running a program, maybe different things. Then that transition, what happens on the system, will change the system state from one state, Xi, to a different state. Then obviously there could be many transitions. Could be many transitions, and to describe the program running on the system. So if we go back to our software security course, some of you took my course, you will be able to understand this. In the software security course, every time for each challenge, I design a challenge for you, which is a binary program. And that program is a set UID program. And that program has a bug. So when that program executes, so we have a system. When you log in our system, you log in as the user CTF, capture the flag, CTF. And there is a file on the file system which only root can access. And in that file, there is a flag. It's a random string. If you get the flag, means you cracked that system. You compromise that system. So at the beginning, the access control rule in that system is like, the subject here is root. The object here is that particular file. The root has the permission to read that file, but no one else has a permission to do that. However, there is a program, it's a set UID program. When you execute that set UID program, you basically introduce a transition to the system, right? When you exploit that CID program, you propose you apply another transition to the system. After that transition, you as a user CTF will be run some malicious code. Maybe the program has bug. You can you have to do a buffer overflow there to run your arbitrary code. And that arbitrary code will execute as a root. So that program, that exploit will be able to read that special flag file. Okay. So in this case, even if you start as a user CTF, you don't have a privilege, but you exploit the vulnerability, and eventually you will be able to read that file content. So you breach that original access control policy here. So you bring a computer from a secure state to an insecure state. Like I said, subjects themselves can also be object, especially for operating systems. Each process, they can be subject, they can also be object. Different object, they can have different access operations defined for them. If a process is an object, then the permission on that object is not only read, write, or execute, or maybe read, write, execute, that makes sense anymore. The permission could be read the memory of that process, kill that process, send a message to the process, send a different message to the process, right? So Linux actually introduced a more complicated system called the capability system. It defines many, I don't know, maybe 10 or 20 different capability categories, since each process, what kind of capabilities they can do to other process and the different other object in the system. So that's much more complicated than the file system one. The file system permissions are simpler. So suppose we have simple access control rights, just read and write, and processors, they can change their own privilege. They can extend its privilege to a larger subject. This can be modeled by setting a copy flag on the access control right. For example, if a right can be copied to someone else, then we can add something. We can just specify that can be given to someone else. So granting rights to someone else gives rise to the principle of attenuation of privilege. So a subject may not give right it doesn't process, it doesn't have. So there are some formal definitions of commands or different operations. So the book we are using actually didn't go that far. So the book I ask you guys to read is called Practical Computer Security or something. So that book doesn't go very deep on those topics. There is another book, if you are interested, I would recommend you to read, is called Computer Security, Art and Science by Matt Bishop. He's from UC Davis, I believe. So right now we are at the second version of that book, I believe. So that book, as the name suggests, Art and Science, it has a lot of formal definition of security and formal proofs of security. Some of the chapters, it's a little bit far away from our real-world examples because they are more formal, they are more abstract, they use a lot of Turing machine-based proving, but it's still an interesting read. So some of the slides are taken from that book, not the book you are reading. Let's say we define some primitive commands here in a DAG model. The first command is create an object. Then this object has no one can access object. So in this case, so the subject basically is not changed. Previously, the subject include SI, all the subjects there. Now we enter a new state, I plus 1. The subjects do not change. So SI plus 1 is just SI. However, the object, we introduce a new object, which means the new object set, O I plus 1 will be the old one with the addition of the new one. Then for each subject, so for all the subject, so this one means any, for any X that is in the subject list set, so all the subject, then we will say the access permission for X to access that object will be empty. So there's no permission to do that, right? So this is how we formally represent this. Then for any subject, all of them, and for any object, for any other object, which is not the new one, then the access permission we just copy from the old one. So this is how formally we represent, create a new object which no one can access in this formal model. Okay, so the math part looks a little bit intimidating at first, but if you think about what it is doing, it's just super simple. So that book, it has a lot of formal definitions like this because it will do mathematically reasoning about the security of the system later. So you can imagine if we create a subject which do not have any permission on objects, it will be something similar. Okay. So if we want to add a right to an object O for a subject S, so basically in the new state, in the permission, so this A here, we write it like a matrix, right? So this is kind of like the access control matrix. And the rows are subject, the columns are object. So we just add a permission to the old one. That's it. So if we delete one, we just remove one. We can also destroy subject, also destroy objects. Based on this, we can create a little more complicated rules. So those are the very basic rule. Create an object, create a subject. Now we can create a little bit more complicated rules. Subject S creates object O, then create object O with no permission. However, because S created O, then S will add its own permission to this object. Then mathematically, we can write this like this. Okay. So like I said, this is not really in the book. I recommend you guys to read, and in the exams, we're not going to do something like this. So this is just a mathematical representation for what I believe you already understand. Okay. Let's say this one we can skip. Okay. So DAC in Linux file system. So for operating system, obviously the access control is enforced by the operating system itself. For Linux, there are multiple different access control enforcement modules. One is for the file system, one is for the runtime environment. So files in Linux systems, they are identified basically by something called iload. Iload is stored on the hard disk and loaded into the memory. Permissions are stored in the iload. Also, a directory is a special file. So directories, like we said before in my screenshot, directories they also have those permissions. So those permissions are stored in the directories iload. Okay. Each user in Linux system, they have a unique ID. Root has the ID 0. Then each user can be a member of one group, and with extensions, it can be many groups actually. Subjects in this case are not necessarily the user directly, but more like the process running on behalf of the users. Each process, they have the user ID and also group ID. So if you took my software security class, you know this is much more complicated than that, right? There is effective user ID, there is real user ID, and the file system where the kernel will use effective user ID to check the permissions. So if you want to learn more about that, you take my software security course. Objects, they are files, process, pipe, many other things. So this example, we actually already saw this. So why the Linux file system is a discretionary file system? It's because users can change the permission. And there are several commands you can use to change the permissions for files. One is change mode, which can change a file. You can add the permissions for user, as long as you have the permission to change that. You are, like, say you are the owner, then you can add the permission for groups for everyone else. Or another one is just a change owner, CHOWN. So to use change owner, you need to use root privilege to do that. To change mod, you just need to be the owner of that file. Linux system, there is a super user, which is root. So basically, root can do whatever root wants to do. So root is not really confined by that access control matrix here. It's basically the god in the system. Many Linux systems, they support access control list, like I said, like using the command set FACL or get, you can change or get the current access control list. This is called the extended ACL, and the traditional permissions are called the minimum ACL. So what is secure in the context of DAC? Basically, a secure system doesn't allow violation of policy. So let's assume at the beginning, the system already has a access control matrix. It doesn't have to be stored somewhere. It's just logically, there is an access control matrix. And that matrix already has all the rights we want to have. This should not be updated. It should not be changed. We define a leak as some transition, some commands that can add a right to an element to a subject which do not, or subject that do not have the permission of that right before. So we say a system is safe, means no one can violate the access control rules. So they cannot compromise the system. So like I said, in the software security course, the example I gave you, in that example, the users, they basically can compromise the system, can read the flag they should not be able to read, and which means the computer system is not secure. So someone proved this back in the 70s. So how many of you took a class like computational theory or introduction to computational theory? So how many of you learned like Turing machine, decidability, those kind of things? Okay, several of you. Okay, so if you took those classes, you know our computers can be modeled as Turing machines, right? And in Turing machine, there is a concept called decidability. Give you a problem, whether the Turing machine can deterministically give you an answer yes or no, right? At a finite time. Basically, it will not be running there forever and do not give you anything. So back in the 70s, several researchers proved that in this kind of access control models, they defined what is safety in this case. Then they used the Turing machine model to prove that the safety of those models, there actually is an undecidable problem. Okay, this is actually not surprising. A lot of problems we are doing in real world, they are undecidable problems, which means a Turing machine or technically a computer can never give you a yes or no answer that is correct and or guaranteed to return to you. For example, a lot of machine learning problems, data mining problems we are doing, obviously the computer can never give you yes or no with 100% confidence. Most of the problems are the undecidable problems. So technically, those are not really computer science problems. They're more like computational problems. So this finding is not really surprising, but if you are interested in how they prove this, you can check the book, Computer Security, Art and Science. Yeah. So, something interesting is we talked about those formal models. You use the models to prove whether the state of a computer is secure or not, or safe or not, is not decidable, basically. However, those abstractions are far away from our real-world systems. Like most of you can understand what we're talking about today, but just only several of you took the Turing machine class, but you can still understand that, right? So it means you don't have to understand all the models to understand the security itself. So before we go today, I want to talk a little bit about another access control model, which is called MAC, mandatory access control. So in MAC, users are granted privilege at the beginning, then they cannot control or change those permissions. For example, we have many files. Some of the files we say this is top secret. And only people with top secret permissions should be able to read those files. No one else should. And technically, there is no owner of those files. Since there's no owner, no one can change that permission. So this is different from DAC. So this is very useful for military applications, also used for operating systems with many multiple users sharing the system. Linux, there is a Linux project called Linux, Secure Linux, or maybe it's called Secure Linux. Anyway, it's Linux. As you can see that this is Linux logo. So Linux mission was to implement MAC in the Linux kernel and allow users to define very complicated security policies, granular permissions for different users, programs, process, files, and devices. So Linux is a very influential project. It has been used in many different places, and also a lot of research on top of that, security research on top of that. So in Mac, the security policy is system-wide. It's not specific to any file, and it's not specific to any users. Owners will not be able to change those. And also, there are many different models that we would say it's a mixture of Mac and DAC. Our model operating system, we can say DAC here. We can also say a little bit Mac here. Some of those research in this area has been quite old. Back in the 70s, there are several papers talking about confidentiality models and also integrity models. We are going to discuss those two this Friday, actually. So those are very traditional topics. Access control model is not that hot area anymore after decades of development. Also, Friday, we're going to look at another very important model called role-based access control. And that was proposed, the model was published back in, I remember it's 80s. Actually, it's my academic grandfather, basically my PhD advisor, he come up with a role-based access control model, rollback. So we are going to talk about that this Friday. Cool. That's all for today. Any questions? So they store with the subject. You go what? Well, that's a different thing. So how do you store that? you can store with a subject, you can store them as a centralized place, you can store them with object, right? Then no matter where you store, you can implement different models. You can still implement DAG or MAC. So if it's DAG, then they will be able to modify that. Yeah. I think Linux is quite close to a complete Mac. Yeah, the design goal, its mission was to bring Mac to Linux. Yeah. So when new object or subject is added, they will be granted some kind of permission. So that process is actually what we call authorization, right? Then after that, we don't change that. Yeah, or basically there is no the owner of user anymore. But back in Linux, the owner is a very important concept. If you own a file, then you can do anything with it. So the Mac, the basic idea there is no concept of owner anymore. The policy still can be changed, but it's not like it can be changed by the owner. It can only be changed by, let's say, the God in Linux, which is root. Yeah. Yeah. Any other questions? Okay, so if you have a M1 or M2 Mac and you cannot get a homework 2 done, just let me know and also let the TA know. We have some solutions for you. Basically, we just want you to install something on your Mac and run locally, so you don't need a virtual machine for the homework. Cool. See you on Friday.